A very good morning, everyone present here. Develop a passion for learning. If you do, you will never cease to grow. thank Dr. Love College. I take this opportunity to welcome you all to fourth technical session on the topic parametric test. Firstly, I would like to welcome today's resource person, Dr. Nancy D'Souza, Professor of Psychology, Ranganath College, University of Mysuru, on behalf of Shagari College, Department of Commerce and Business Administration, ED Center, I welcome you, sir. The one who acts as a support of strength recognition and passion with narrowly in all activities of the college is our beloved principal, Dr. Ray Kyle. Let me welcome you all to this session. I extend my heartfelt welcome to Professor Satyanarayana, the Department of Commerce and Business Administration, to this session, sir. I welcome you, sir. I would like to welcome to Dr. Jyoti Ray, Head of the Department of Commerce and Business Administration, to this session. I welcome you, ma'am. I also extend my warm welcome to all the participants of this faculty development program. I welcome you all. I also welcome all the faculty members and technical team to this virtual platform. Once again, I welcome you all. Thank you.
Good morning, everyone. This is your IT assistant officer, Department of Commerce, Business Administration, Chatham College, Mysore. So, on behalf of Chatham College, it is with great pleasure to introduce our next key guest of this session, Dr. Nancy D'Souza. Dr. Nancy D'Souza was graduated in BC from Nashville University, later continuing his post-graduation in the University of Mysore, and served for 5 years PhD from the same university. Also by from Unama University. At present, Sir is working as Professor of Psychology in Maharaj College, Mysore. Sir is serving as Board of Studies and Board of Examinations and Academic Science of Sir has extensively worked on shyness as a first area of research and is also working in relation to social media and sleep quality for students, both professional and non-professional courses. Sir has already published 250 articles in national and international journals, where he is the economic board of 7 journals. And Sir edited 4 books on emerging trends in behavioral sciences. And successfully, Sir guided 4 students for doctoral degree, especially in the area of psychology, technology, and forensic sciences. At present, he is guiding 12 students for a doctoral degree. Sir is the recipient of prestigious and President's Gold Medal Award in the year 2017 for excellence in psychology. And additionally, Sir was the principal investigator of UGC funded project on shyness and is the research consultant for several institutes in Karnataka and also other states. So thank you for giving this opportunity to introduce our place chief guest gallery. Thank you.
Thank you, sir. Multiple cases of the life and this Nancy sir take over the session.
Good morning, allowed to share the screen?
Yes, sir.
Yes, sir. Can you hear me?
Yes, sir. You can share.
Now, can you still, okay. Sir, okay. Good morning, everyone present tonight. This is Dr. Nancy D'Souza from Knowledge College, working as Professor of Psychology, and I will be dealing next 2 hours on application of parametric statistics in research. And since the title is going to be more on social science, so few of the examples which I quote is basically from the what we call subject social sciences. So to start with, because one thing what I've seen in my last 2 to 3 decades of my service, that people are scared of statistics. I don't know why. The idea here is the attitude towards statistics matters a lot. People usually get confused with the statistics and mathematics. To make a particular clarification towards that, please understand statistics is not mathematics. Yes, mathematics definitely many people find it tough, but statistics is applied part of it and a very simplified part of mathematics. So the idea is don't have the idea thinking that statistics is tough. It is not statistics is tough. Our attitude towards statistics is tough. So change that attitude. So anybody can master statistics, anybody can manage statistics. Only thing is people do little hard work and little smart work and little more theoretical background if you have it. So people usually have a wrong conception of statistics. People just think that statistics means just what you call calculations. No, it is not just calculation. Statistics is a process, and the process begins with the collection of data and ends up in interpretation of the data. So, basically, in statistics, the definition goes like it's a process comprising of collection of data, compilation of data, analysis of data, and interpretation of the data. In short, collection of data can be in terms of primary or secondary data collection techniques, which are not much over it. Compilation is how you prepare your data for analysis, either for manually or electronically or online or offline. Then analysis of the data refers to how you analyze the data, having some of the rules and regulations in mind. And the last part, which is basically whatever results have been obtained, they have to be interpreted accordingly. So, entire these 4 sequences, what we call constitute for the idea of statistics. So, this is just a given what we call idea about statistics. Next, we move on to the measurement part because ultimately, all of our talk will be based on parametric statistics. So, when you talk about the measurement and we give a specific type of data, measurement goes in 4 levels. Nominal level, ordinal level, interval level, and visual level. Nominal level, we know when the data. Not really. Okay, that is other than full mode of calculation. So now it's done. Okay, so when we talk about the nominal level of scaling, it is just what is the designation of assignment of a number, which is not particular to number. And in the second stage, you put it to order, like you rank them. And in the third stage, the ranks are given appropriate intervals, so that each interval is particular exact same as the other interval. So that is to control the levels of the scale. And finally, the ratio level of scale where all the measurement is perfect, because there is a Lacanian interval scale where you find an arbitrary 0 or 0 is not fixed. But remember, when we talk about measurement and parametric statistics, usually we move on to interval or ratio level of scaling. We cannot perform any parametric statistics with the nominal or ordinal levels scale. So the lot of researchers are listening to me. Please first classify your data, whether your data is in the form of which of these particular scaling measurements, whether it's a nominal or ordinal. So if it is nominal or ordinal, preferably you have to go for particular non-parametric statistics. And when it comes to intolerant ratio scale, please understand, even in intolerant ratio scale, when the data is continuous, but again the condition applies that the data normally has to be followed. So lot of things we are going to discuss. So first identify your data, what level your data is, nominal, ordinal, or intolerant ratio. So first condition is that your data should be on an interval level or on a ratio level of scaling. So now move on directly to the parametric statistics. The idea of this parametric is you derive additional parameters. So what do you mean by additional parameters? Because this cannot happen with the qualitative data. This can happen with only quantitative data. So when we talk about the quantitative data, so technically we refer it as a parametric data. For a set of parametric data, we have a set of parametric statistics. So the idea here is these tests are a set of statistics for which we have prior knowledge of the population distribution, we know the variance, and by chance, even if we don't know, we can read later, we can approximate that particular the knowledge having the normal distribution confirmation. Then, when we talk about parametric tests, remember from a set of data raw scores, we can derive a fixed set of parameters. Then later we can determine what is our probabilistic model. So the idea is even it can be used for various types of testings. For example, it could be used for difference-based testing. It could be used for relationship-based testing. So we are going to discuss based on some of the issues, and one of the important things is when we talk about normal distribution, also we will be bringing things in. Where the normal distribution is the thing to consider whether to go for a parametric test or non-parametric test, and which can be possible with the help of central limit theorem. So before getting into the actual parametric and non-parametric test, let us have a simple understand simple difference between parametric and non-parametric tests. So if you see when we talk about distribution part, all of us are about normal distribution or a bell-shaped curve. So usually we apply parametric tests on a continuous data where the data distribution is normal. You don't find any skewness or kurtosis. Much of this, some amount of skewness and kurtosis are applicable, but not too much. And the same thing when the decimal distribution is there, or when you get a non-normal distribution, then you cannot apply a parametric test, but go for a non-parametric test, though your data is parametric. Then, as I already said, parametric tests are suitable or applicable only for quantitative data, whereas non-parametric tests are usually applied for qualitative data. Then, as I said about interval and ratio levels of scaling are used for parametric tests, whereas nominal or ordinal scale measurements are used in non-parametric tests. So, what happens in parametric tests, we get mean, FT, and other things, where here we get frequency and percentage. But in general, it is said that parametric tests are powerful because we use the original data, whereas non-parametric tests we just use the frequencies, or even if we use the data, even if we use the continuous or parametric data in non-parametric, that will be converted into ranks or signs. So automatically it is said that non-parametric tests are less powerful. The idea here is, though we talk about that it is less powerful, to be frank, even sometimes we have no other option unless otherwise we have to just end up with nothing. So even non-parametric tests tests are also important when your data is in the form of quality rather than quantity. So these are the prime differences between what we call parametric and non-parametric statistics. However, in general, I'm not going to talk much about non-parametric statistics. We will be talking more on parametric statistics. So now, what are the assumptions? Because before we start any statistics, we have to have some assumptions. So first thing itself, as again I'm repeating, the population data must be normally distributed. So for that we are going to talk about normality check later. What to check is normality. Then observations must be independently safe. Why? Because the observations cannot be dependent on other things. So each observation is independent of other. The next one is population must have same variance. That means what the variability across what we call different groups which is drawn from the population, they must be same. If there are different what we call variants are there, then parametric tests are not suitable. Then the samples drawn from population must have a homogeneity principle. This is also important. Why? Because when we talk about homogeneity principle, if the data is too much of heterogeneous, it leads to a lot of outliers. So once there are outliers, whatever the data obtained, or sorry, the analysis what we have obtained may not be what we call applicable to the general population because too many outliers spoil the significance and the analysis. So in such cases, it would be preferable to go to the other side as non-parametric. And as already I said, the data should be on ratio or intercept to the final two levels of measurement. Now, all the time we are talking about normal distribution and normal distribution automatic test. So if that is the case, you may have a lot of curiosity. What is this normality check? So and what is this test of normality? To get a simple idea, so whether it's online or offline, there are two types of tests which are regularly used in what we call measuring what we call the deviations or the tests of normality. Now, when we talk about the test of normality, two tests are usually employed in research. One is a Shapirovic test, and another one is Kolmogorov-Smirnov test. And both are available online as well as offline, and various software they are available. So the first thing is before getting into your analysis, the first thing, and if the data is whether the data is quantitative, continuous, then invariably you have to check this data for the normality check. Why I am insisting on this because nowadays I think most of you are in the teaching profession or are doing research. So we talk about the publication part and to publish in a good impact of journal, UGC theories or Scopus or Web of Science or even PubMed. I think there are a lot of scrutiny in your articles to be published. So usually they look for whether the author has done what you call a test of normality. So test of normality, that is why it's important. So before you submit the data in general analysis, especially for quantitative data, go for test of normality by adapting any one of these two tests based on the N. The first test itself is a Shapirovic test. So usually this is applied when the sample size is small. So usually if your sample size is less than 50, it will be advisable to go for a Shapirovic test. Then how do we consider whether the data is what we call common assumptions of normality or not? This is a very simple one. If the test value if you get, if it is less than 0.05 as a significance level, then you automatically have to switch over your data analysis to the non-parametric side. So that is what the obtained test statistics by what we call the Shapirovic test should not be significant. That is it. So if your test value is significant in the normality testing itself, that means automatically you have to switch out to the alternative non-parametric test. So if n is less than 50, then the test is used is the Shapirovic test. And if n is more than 50, so you apply Kolmogorov-Smirnov test. So principally same, only the what we call the tests are different. Shapirovic for the smaller sample size, that is less than 50, and if the sample size is more than 50, please go for Kolmogorov-Smirnov test. In both the cases, the idea is same. Your test value should not be significant. Please make a note, your test value should not be significant. If it is significant, then you cannot use the parametric test. So that's the rule. So this is regarding in short about the test of normality. Then usually why we have done this parametric test? It is basically for testing the hypothesis. And how the hypothesis testing goes. I will try to explain that in a single slide. Uh, when you have a particular hypothesis testing, and I'm not going to talk much about hypothesis, think of only three types of hypothesis: null hypothesis, alternate hypothesis, and direct hypothesis. So we need to test the hypothesis because you may have what you call formulated the hypothesis in the beginning, maybe during introduction or methodology, and later you have analyzed in the result chapter, but later you have to verify. So for verifying the hypothesis, you need hypothesis testing. So how it goes? So we start with the problem definition, what are the segment of the problem. Then the idea is now better we clearly state null or alternate hypothesis, and sometimes it could be directional hypothesis that also can be done. So once you have what you call one of those types of hypotheses, now you start collecting the data. So once you are collecting the data using the appropriate tool, now based on the what you call assumptions of normality, you select what you call the relevant test and the appropriate probability distribution. Now, probability distribution here refers to the significance level, whether you want to check at 0.05 level or 0.01 level. So that is explain what is this 0.05, 0.01, and 0.001 at the end. So many times we get confused what is the significant, highly significant, and very highly significant. So now you have chosen the test, and once you have chosen the test, you have determined the significance level also, what you call 0.05 or 0.01. But usually our universal standards are to fix at 0.05 level of significance or 95% of confidence. Then nowadays the software use the direct critical value, or you can refer the what you call textbooks, and behind each text, the end of the text, there are book of statistical tables. There are what you call many statistical tables are there at the end. So with the help of degrees of freedom, either n-1 or n-2, depending upon the test. Because sometimes it is n-1, and let you know when we're discussing a particular test. So n-1 or n-2. So you determine the degrees of freedom, and later you have to see whether this 1 or 2 test, that is that of where you have fragment directionality, then it becomes a 1 test, and if you think that equivalence is there, then you can go for 2 tests. Then once you have the critical value, once you have derived test value from your experiment or data collection, now you have to compare what you call test statistics with the standard value, that's a critical value. Now, if your test value exceeds or equals the critical value that's given the text data, then you have to reject the null hypothesis. So that means whatever you said is not happening, that means the value is significant. So in such cases, you are going to reject it. By chance, what your test value is below the critical value is given from the text or from the software, then you cannot reject the null hypothesis. But please remember, when you formulate a hypothesis, to the rest we are going to use for hypothesis testing and verification, it is said that again, null hypotheses are meant for rejection, and alternative and directional hypotheses are meant for acceptance. By not doing so, we may commit technical errors like type 1 and type 2 errors. That also we are going to discuss eventually. So, in statistics, when you talk about the testing part, the entire testing part can be seen in following ways. Either the test which you follow is going to be parametric, or test you can follow is a non-parametric. Within parametric, you may have a difference-based test or relationship-based test. The same thing would be there for non-parametric side also, difference or relationship. But for our today's talk, we are just what you call restricting or talk to the parametric testing. In that we are going to talk about difference-based test as well as test as well as related to this test. So these are the things we are going to discuss in detail. So we are going to start with the parametric test of difference, that is more important, followed by parametric test of relationship. So now we are going to start with the particular parametric test and the difference based test for two groups. Whenever I talk about the two group testing on a parametric side, please remember we talk about t-test. But if you see the slide, now there are that test also. So there are particular three types of t-test we will follow under t-test classification along with the z-test. So in difference-based test, especially when you want to find out the difference between two groups, the idea here is when two groups you want to compare based on different conditions. It could be independent sample test, or it could be paired sample test, or it's a one sample test, or it could be Z test. So we'll be discussing one by one. So for easy understanding, we start with the Z test first. Then we can go for the three types of T tests. So the starting the first Z test. And remember, in Z test also we have got two types. Z test for a single sample as well as Z test for two samples. So, what do you mean by single sample is what you have only single sample to be, but you can check against the other way which will be discussed at the Z test for single sample. Suppose there are two samples are available from the population, then we can further apply Z test for two samples. So, what is the nature of it? So, we'll go one by one the nature of it. But please remember, Z test is applied when the sample size is more than 30 or a mean difference. So, for a smaller sample size, we do not apply Z test. We apply Z test for usually a larger sample size, preferably more than 30, and that is the rule. And we see the pictorial representation in a single sample test, particular, we use particular population values with the single sample combination, or even in the test for two samples, we give the calculate Z value and we try to find out the Z value so that your minimum Z value should be 1.96 either on the plus side or on the minus side. So which is supposed to be significant at 0.05 level. So Z test would act as particular one of the tests where the sample size is more than 30 for establishing a mean difference. So when we use, so that test is a statistical procedure to test an alternate hypothesis against a null hypothesis. If alternate hypothesis there is a difference, a null hypothesis there is no difference. Okay. Now it is particular used to determine the two samples are different when the variances are known and sample size is large. The variance here I'm talking about standard deviation square because it is sigma into sigma, that is standard deviation into standard deviation is equal to variance. So when you know particular the variances are known and sample size is typically more than 30, then it's nearly available to go for a Z test rather than particular rather than T test. So remember, it could be two groups taken from the sample taken from the one population because you know the population varies. So based on that, we can use a formula which I am going to show you later for one sample as well as two samples. And what are the conditions of when do we use? So usually we use Z test when the samples are drawn at random because you draw independently two samples from the population at random and then you try to establish a mean difference. And whichever samples are taken from the population, they are not connected to each other. Sample 1 to 10 within the particular group 1 are different in themselves as well as different from group 2 where again there are two samples 1 to 10, 1 to 30 or 1 to 40. They are not connected at all and they are not related to each other. That's why all the samples are taken from the population must be independent. And either you should be knowing the standard deviation because later is variance, that is standard deviation multiplied by standard deviation. So when the standard deviation is known, or if there is an option to calculate, still you can go for a Z test. And as usual, I said the observation is large, then also it can be used. And when one sample is there, this is the formula. Z is equal to mean minus mu 0 divided by sigma by square root of n. I have not calculated any workload sample because of the time constraint. So, but I'm just showing the formula for it. Z is equal to x bar, or if you see x bar, that is mean of the sample which you have. As I said, we already know about mean of the population, that is mu 0. Then sigma also we know that the standard deviation of the population, and n is the square root of n, where by n we are considering number of observations. So if you know all these things, and if your value is 1.96 after calculation, if you derive that value of 1.96 and above, then you can say your what is called mean which are obtained from the what is called sample is different from the population mean. Or if the Z is coming less than 1.96, then you can say your mean is the population mean. There is no difference. So this is basically done when you have what you call one sample, your sample against the population mean and if you are checking, then this formula will be good. But again, I am underlining the condition is sample should be larger than 30. So this is then what is the idea for one sample testing. Just okay, I have given one example. So a principal at a school teaches school above average intelligence, the students are bright. So then he calculates what is the IQ of the student and he gets what is the mean score of 102.5. And remember the mean IQ, the range of IQ is 90 to 110, and on an average the mean IQ is at 100. So against 100, the student IQ scores are from 102.5. Now, whatever the principal has said, can we do it? Because principal has already claimed that students are above average. Now, we know the particular sample mean that is 102.5. We know that population average is 100 IQ and standard deviation is 15. So, using this and using the formula which is already shown earlier, we can see whether the sample mean is different from the population mean or different. If it is same, then okay, principal's claim is wrong. And if it is different or it is significantly different, then principal's claim is right because there is a 12.5 difference is there, and this might come as significant one. So anyway, this is for what is just for an example I give. We go to the next particular when okay, we are calculated that. So for this set of data, where we set principal size 112.5, the population mean is 100, and already standard deviation you have put 15 and 30 samples for minimum. So you have ended up with 4.56. So a value of 4.56 is that. Any doubts there? Sample now we have got a Z value of 4.56. Which is definitely 1 point significantly more than 1.96 because you can see the values which are required at 0.5 it is 1.96 and at 0.1 it is 2.58. So definitely we can say that mean difference of 12.5 with the sample mean to the population mean is significant. And please understand, there is a difference of 12.5 from the population mean because the population mean is 100 and the derived mean is 102.5. You get a difference of 12.5. So using this formula, you get Z value of 4.56, which is definitely more than the expected value in the 1.96 at 0.05 level or 2.58 at 0.01 level. Thereby, we can say whatever the principle has claimed is true. So this is how you interpret that test for a single sample against the comparison in the population mean. Then we continue further with the test for two samples. So when you talk about that test for two samples, remember you get two samples from the population, minimum populations. So the formula is slightly different now. So last time we had a very short formula, but this time we have formula with a slightly different. Now the z is equal to x1 minus x2 for the means of what you call samples minus mu1 and mu2. You know that what you call population means or the difference between the hypothetical population means. Sigma 1 and sigma 2 are the standard deviation of the two populations. N1 and N2 are the sizes of the two samples. So now you can do what is called whether two normally distributed independent populations are significantly different or not by using that test. So that is what you need a mean difference between the two means. You need a mean difference between the population means. You require SD of what you call the first group. You require SD of the second. Sorry, sigma and sigma 2 SD of the first population and the second population. And typically you require N1 and N2. That is the number of subjects or the samples in each group. So by using this formula, that is again mean 1 minus 2 minus population mean minus mean or the hypothetical difference divided by sigma 1, that is the standard deviation of the population square by its N1 plus standard deviation of the population 2 by its square of that divided by N2 and take entire square root of it and you simplify, you get a Z value. Again check against at 0.5 and 0.1 level whether it's 1.96 or 2.58 and if it's less than 1.96 we can simply accept the null hypothesis there is no difference. But if the value Z value of field is more than 1.96, now we can reject the null hypothesis and accept the alternative hypothesis. So this is the idea that test for one mean or that test for two means. So you can do either of them. So they are much easier. Now this are talked about when sample size is more than 30. If the sample size is less than 30, then invariably we are going for independent samples t-test. Actually, this independent sample t-test is a new nomenclature for student t-test because this test goes by several types of names. So initially it was called a student t-test because the test was founded by one of the professors called as Professor Gosset. But he didn't want to put Gosset test, so he gave a nickname like t-test. So later the nomenclature is changed. Then they started unpaired t-test. Because why unpaired? Because n may be same or n may be different in two groups. So that's the idea. But in both of those, sample size must be less than 30. So because that's a two different number. So that's why the word is unpaired t-test. Then the word came two samples test because when two samples are different. So and you want to establish a mean difference and find out whether that mean difference is significant or not. Then they use the word two samples t-test. But the latest nomenclature which you find in the new textbooks and it is independent samples t-test. The meaning is very simple. When two samples are drawn randomly from the population and you try to establish a mean difference, then that is called as independent samples. The what you call two samples are drawn randomly. So now some of the text we are clearly regarding that. So So you have a test. Again, the measurement is contained level, either interval ratio data, and as the condition prevails, normality should be followed. Then it compares two means randomly drawn. Then the test to be used when two separate, independent, or identically distributed variables. Now I'll show an example that will be easier. As I said, the test has to be applied when sample size is less than 30. As usual, if it's more than 30, we already discussed about it, the set test. Now, what would be the best example? You have a group of people randomly drawn from urban area, and you have drawn a group of people from rural area, and you are trying to measure the aptitude or the attitude, whatever one dependent variable you want to check between these two. For example, nowadays the governments are giving a lot of what you call free schemes. Now, what are the attitudes of what you call so-called schemes put in various ways? When we talk about those various ways of scheme, we are given free schemes given by the government. What kind of attitude urban people will have and the rural people will have? So in such cases, you have got two groups, and you want to see whether which group is more favorable or unfavorable. So you want to go for a mean calculation, and then later you try to what you call establish a mean difference between them. And once you establish that mean difference, and you are going to check whether this mean difference is significant or not. And that job will be done by independent sample speed test. Now remember, when we talk about independent sample speed test, usually we find in all the statistics the calculation of DF is n minus 1. But in this case, when we talk about two groups difference or independent sample speed test, the DF will be n minus 1. So researchers who are who are into research, please note down here the DF will be n minus 2 rather than n minus 1 because you have two different groups and one n minus 2 because from each group one DF will be taken out. So now it is not n minus 1. N minus 1 from each group, so ultimately it will be n minus 2. So the other example would be what you call difference between male and female students in their academic achievement, or a difference between arts and science teachers in their teaching skills. Now, remember one thing is you literally get a key value and you try to what you call describe them. Remember going back to our statistics, definition, collection, compilation, analysis, and interpretation of the data. Now, while interpreting, you have to be very careful. Suppose you are interpreting urban versus rural. If the particular difference is significant, and that significant and more mean value comes for urban sample than the rural sample, then the interpretation should be that the mean difference between urban and the rural samples in their attitude is significant. I'm underlining the word the mean difference. It is not that urban respondents are significant or rural respondents are significant. I've seen some of the writers which are very wrong writers or wrong interpretation. It is not that one group is significant. It is difference between the two groups that value is significant. It is not urban is significant and the rural is not significant. It is not that males are significant or females are significant. It's not that science teachers are significant or teachers are not significant. No. This way interpretation will not work, and we call that as a wrong way of interpreting the things. So you might get a revision for that later from the examiners. So it is basically when you explain, it is the difference between them is significant or not. So that's where your interpretation lies. So moving to the next, okay, I think I have to show the formula. Okay, in the given sample, the formula is like this. One of the formula, there are different formula available. I'm using the regularly used formula because of time constraint there are varieties of formula available, but I'm just taking linear density base for calculation of t value. So to calculate t value, you require both the means mean 1 minus mean 2 because two independent samples are being derived. You require both the n's, n1 and n2. You require both the ST values. So if you have got these 6 parameters with you, then the t test will be easier. So how the t test will come? Mean 1 minus mean 2 divided by square root of n1 minus 1, that's sample 1 minus 1 into sample 1's ST square plus second sample n minus 1 into its ST square divided by n1, that's the number of observations in the first sample, n2 number of observations in the second sample, that you add it and minus 2 into again square root of 1 by n1 plus 1 by n2. It's a simple formula usually applied when your sample size is small. Other formula are there, but then you have to explain because of the time constraint. So now you understand what you how the tests are being used. So now compared to that test, there is a slight variation is there. So just have an observation later because this people will be shared later for all the participants by the organizer. So you can check it and you can find more clarity in that. So the next part, okay, if you are clear about independent samples, very clear two samples drawn randomly from the population. And you try to establish a mean difference between them. I think I have done examples. So that should suffice along with the formula. The next one will be paired samples. Now suddenly we are doing a paired samples, paired samples. So when you talk about paired samples t-test, the idea is it's a repeated measurement on the same region of the sample. So that means what? Suppose you have what you call you have a data which is in the form of pre-post design, which you have what you call have data in the form of before after design, or you have data on the same individual which have been collected repeatedly either simultaneously or successively. Now, what do you mean of simultaneously? For example, if you have got what you call students' data on language 1 should be out of 100, and same students' data again should be out of 100 in language 2, say English and Kannada. Now, there are match samples for two subjects, but remember it should be matching because when you talk about independent sample t-test, I use the word unpaired t-test. That means what? There will be unequal numbers in the sample size. Group 1 may be more, group 2 be less. But in paired samples, something what happens, the same sample is exposed twice or second time considered, here n must be same. So since n must be same, that means the same sample is exposed twice. So that's why it's called as paired samples. As I said, it's a pre-post design or it's a match sample for two subjects provided baseline measurement is same. Like if language 1 is scored out of 100, language 2 also should be scored out of 100. But just if language 1 is scored out of 50 and language 2 scored out of 100, now either you have to convert language 1 into 100 or you have to reduce language 2 to 50. So that's how we have to match the two. Then we can apply what we call the paired samples t-test. Now, what it says is there any difference from what we call between two different time points? For example, when we talk about before and after measurement, or suppose you are giving a training session for your students, suppose you have taken a set of slow learners and you think that they are learning very slow. So you have developed a new practice for them to learn fast. So what you do, you have a pre-test and you have got your protocol for improving their learning, that is for next 3 months. So you have given to them, you are actually involved with them, and again you measure their learning capacity. So same test you are given, which of the test you are given in the pre-test, and this be repeated in the post-test. So Now you can see whether in the post test they have scored very high or they have scored high. Now, and whether that score difference from free to post is significant or not. So, in such cases, you can go for a pair samples t-test. So now go to little theory. A t-test for repeated cases or t-test for match samples. Now, the idea here is the two distributions of different variables are highly correlated. Why? Because whatever the previous scores are there, and there will be find an increase in the post test. So those who score high here might be scoring high there also. So those who score here may also score more. So that could verify the scores could be correlated high. Then one important thing is one-to-one correspondence between each subject. That is what subject A is measured here, same subject measured again. Subject B is measured here, same subject again is measured. So suppose you have got 15 subjects, the same 15 subjects have to be measured again, and their scores have to be connected. That is more important. That's why they are called as matched pairs. Then remember, again one more condition is whatever the data you have obtained on a quantitative testing or the initial testing, not for the post testing. Because in post testing you want to expect some change, and the change could be either on the complete on the positive side, and now the scores could be biased for the post test. So post test is a what it has got an influence of what it the intervention. So there could be increase in all the sample scoring. So in such cases, normative test will be done only for pre-testing, not for the post. So please remember this concept in your mind. So if you have seen the picture, if you see the same sample, if you have seen one to one, that's what I showed you. Only the time cap will change after some time you test. So one to one corresponds between each subject in the group one and the matched pair in group two. So same this one. This is where what you call you have to be very careful. Then you are going to check whether the mean difference you should get between the pre and post is significant or not. Again, making a correction. It is not that pre-test is significant or post-test is significant. It is difference between doing two testing. Whatever the difference you get, that should be significant or not. That should be decided by the pair samples pre-test. The formula is quite simple. If you are using the formula, remember here is your T is equal to D bar. That's the difference between the means. It is not just or it's mean difference one minus difference mean of pre-test minus mean of post-test. Will combined we call it as difference between the means. Then ST is the standard deviation of the difference, not the particular. Not the ST of one group or ST of the two group, it is standard deviation of the difference. So you take the difference of pre to post, and for that difference, you calculate the standard deviation, and that standard deviation will be what you call used as in the denominator, and that will be divided by square root of n, that is what you call number of cases. Now remember, SSL plus square root of n is also used the terminology standard error. So in another words, T is equal to difference minus 0, that hypothetical 0 divided by standard error of the difference. Now how the standard error of difference has come? It is you calculate the SP divided by a square root of n, gives rise to whatever the T value. But remember, it's a pair sample t-test value. And going back to the degrees of freedom now, remember, in the independent sample t-test, we said it is n minus 2 because you have used two different groups. Since you have used two different groups, so that will be n minus 1 and n minus 1, making it n minus 2. But in this case, in particular pair sample t-test, it is going to be n minus 1. This making F is equal to n minus 1 because it's the same sample we are using again and again. So that is why it is n minus 1. So if you are clear about independent samples and paired samples t-test, the next test we are going for one sample t-test. Okay, in the one sample t-test, here what you are going to do is you check your group mean against an established standard mean. So most of the times you find in what you call medical sciences and because in medicine, a lot of the medical parameters, the standards have been already established. It could be your lipid profile, it could be your hematology, it could be your hemodynamics. So whatever they measure, they are what already standards. So when your group mean is checked against a standard mean or a known mean, which is much popular, so then it will become what we call a one sample mean test. Now, why one sample? Because you are using your sample against a known existing standard mean. So, it is a test to use determine whether an unknown population is different from a specific value. Because you are taking a value, think that again going to a school performance. You are given an extra coaching for the student, and you fix the standard because the standard may not be other than existing. Even a researcher in consultation the expert can fix the standard, and you expect that the student should score 75 and above minimum because of the coaching you are given. Now, what you can do is you can train them for 2-3 months, give the test out of 100, and whatever the means the your group has obtained, that can be treated against 75 as standard. Remember, you have to treat it as 75 as standard and see whether your group means either equal to 75, less than the 75, or more than the 75. Now it is very simple. You are checking your group mean against the standard mean. So once you are doing that, understand the part that the interpretation is very easy. Why? Because when you talk about one sample, so if it is less than the standard, that means you are not able to achieve what you wanted to achieve. If it is equal to the standard, that means if there is no difference between your mean and the standard mean, then that means you have achieved enough. Whatever the goal is there, you have achieved. Sometimes what happens, your group mean is more than the standard mean. That means the group has achieved more than what is expected to achieve. See how simple is the interpretation part of it. So once you do that kind of interpretation, it will be very easier for the particular examiner or the readers to understand. Now remember, when you talk about one sample t-test, it has got a lot of advantages. So what are those advantages? The advantages are like, rather than going for another control group, because suppose you don't have a control group, then in view of the researchers, you should have an automatic group, or we call it as a waitlist group. So in the waitlist group, what you have is a control group. Usually a control group is not given in intervention, whereas the test group is given intervention or the treatment, and later you check the effect. Of course, the waitlist group is the waitlist group with the control group is given the same intervention after the data collection is over. That's the issue. So that's one thing. So in few of the researches where the standards are already available, you don't require a control group because control values already exist. So once the control values already exist, then you don't have to use what is called a control group. Lot of time and money will be saved, and same amount of time and money you can increase or invest on the test group or the group which you are working, so that the reliability of the results will be increased further. So that's it. So on a tutorial format, assume that population from which the collection sample is normally distributed. So whether what is the difference between the sample that's what the outside of the global mean. So you can check with that what is called the observed mean versus the standard mean. So if the difference exists, On the lower side, then you are not achieving. If it is same, then it is accumulated or it is you have reached the standard. If it is more than the standard, then you have proved as outcome of the standard. So that's the interpretation supposed to be. And how it goes, the formula is, if you are seeing the formula, it is simple. T is equal to mean minus population P divided by sigma by square root of 1 or standard of the difference. So slightly change from the first sample figure. So here T is equal to mean minus mu divided by standard error, standard nothing but h by square root of n. So now population mean already you know, and x bar which is what you call your group mean, and standard deviation and n if you know, then you can easily calculate one sample t value. And remember here also df is equal to only 1 n minus 1. Not only 1, sorry, it is n minus 1. So that's the idea in what particular one sample calculation. So to summarize the differences, we have 4 tests on the parametric side. One is the Z test for one sample as well as 2 samples. The next one is your independent samples of student t test, followed by paired samples as well as one sample t test. So for 2 group differences, there are 4 tests are available on the parametric side. So this is only when we talk about what is called the 2 groups differences. Later we are going to move in the parametric side when there are more than 2 groups. So usually when there are more than 2 groups, the idea of the compound is the ANOVA. So one of the things which we are going to discuss much and much used in all the sciences is ANOVA. So you see, whenever you have more than 2 groups and you want to establish a twin difference with the additional variables and all, with the more independent and as well as one or two dependent variables, we can easily go for ANOVA. So the full form is analysis of variance, and ANOVA stands for what we call earlier it was restricted only to agriculture, and because the entire concept has emerged from agriculture, and the formula of this particular formula or the procedure is not efficient. So, not necessarily effects or Fisher's ratios. Why? Because in the name of not efficient, we refer them as Fisher's values or Fisher's ratios. And origin lies in agriculture, but now it is used in all the sciences. And very popular procedure. Why? Because it considers all the values in the analysis. It will not leave any single value. So equal weightage or due weightage is given for all the particular values in data points. So hence ANOVA amounts to a very popular method in identifying or finding the significance of difference between more than 2 groups. So we have several types of ANOVA variants are there. So starting with one ANOVA, then we have univariate ANOVA, then multivariate ANOVA, repeated measure ANOVA, and ANCOVA. So we are going to spend much time over this because there are varieties of procedures are there, and your research design might or your hypothesis or hypothesis may end up in using one of these types of ANOVAs. So then what is this ANOVA and what are the particular issues underlying? What are the assumptions to make whenever, apart from the general assumptions of parametric statistics, there are specific assumptions which we'll see one by one. So now remember, as already I said, how ANOVA works. Because ANOVA is basically identifying significance of mean difference between more than 2 groups. So that means there could be 3 groups, there could be 4 groups, there could be more than 4 groups, there could be 10 groups. So whenever there are particular more than 2 groups, invariably we go for ANOVA. So statistics refer this as extension of t-test. Why? Because extension of t-test, because usually we the almost the procedural formalities are almost same as t-test. So many times we are required ANOVA are the extensions of t-test based on independent or paired samples t-test. Now, whenever you what you call data analysis, basically we measure what you call variance, the variance between the groups to within the groups, and then we see whether that is the F value. So once the F value is high, then we say there is a significant mean difference exists. Otherwise, all the means are same. So that's why I said that for the analysis of multiple groups of data, to determine the variability between the samples and within samples, we can invariably use a statistical procedure called as ANOVA. So, if null hypothesis stated as there is no difference and your F value is non-significant, then we say there is no mean difference, then null hypothesis accepted. So, we use the F distribution or F table to find out this, and ANOVA consists of group of distribution functions, a series of calculations. Then usually we find a single field degrees of freedom in other strategies like pre-test or correlation. Usually end up with a single DF or single degrees of freedom, but in ANOVA we usually end up with a double DF, or there are 2 degrees of freedom, one is numerator degrees of freedom and the denominator degrees of freedom. We will discuss as it comes when we will do for a formula, when we will do for formula and the procedure. Now what next in ANOVA? What exactly it does? What you call it basically what you call splits and observe aggregate variation. Because of variation, aggregate variation within the data set, it what you call it splits into 2 parts. That is the systematic factors and the random factors. Now remember, the systematic factors have a statistical influence on the given data set, while the random factors do not. So ANOVA is being used to use what you call how these what you call independent variables have influence on the different variables in a regression study or in a what you call difference-based study. So that's what you call ANOVA does. So now what are the assumptions of ANOVA before we are going for a specific type of ANOVA? Now, as I said, more than 2 groups, that means minimum of 3 groups and more. So, first thing is, as usual, we discussed earlier, a normality check must be there, and your Shapiro will call the Bomogros minimum should be non-significant. Then the variability across all the 3 groups should be the same or near to the same. Then no connecting link between within the samples or between the samples if you have selected the subject, they are independent of each other. Then within each sample, the observation of the sample randomly and independently based on the randomly selected. Whenever factor effects are there, they are additive in nature. Then population must be symmetrical and unimodal. This is not a bimodal or bimodal distribution. Then usually we expect to be equal numbers and definitely greater than 10 in each. But sometimes it's not possible. Sometimes there will be variation. I've seen we have the textbooks where ANOVA is done with the unequal group sizes also. But usually they expect that groups, if the sample is there better and sufficiently larger size, that is at least more than 10 is better. Usually higher the sample size is always better. Then what are the assumptions? Now again, that's what you call. Now come to the variable part. The variable part, what you are measuring, should be at the 3rd or 4th level of measurement. That is interval or ratio level, and data should be continuous. Just so there are examples are there. Then independent variables, minimum 2 variables, independent but split into different levels. So that's also important. They are categorical. Suppose you are talking about gender difference. Now it is not just male and female. Now it is male, female, and transgender. If it is only male and female, we typically involve a t-test rather than a one-way ANOVA. One other thing people do with the 2 samples also, but preferred test is when there are two samples, a difference to be established, then it is t-test. But some data is required, so that will go on what you call the rational. That is keeping apart. So in general, we use what you call minimum of a different variable should independent variable should be split into three levels. Like if you I split gender into three levels, it is male, female, and transgender. So that's the kind. Or if you are going for what you call ethnicity, Pradesh, African, American, and Hispanic, or physical activity. For example, four groups like the sedentary group, wanted and health groups are there, or profession, surgeon, doctor, nurse, dentist, therapist. So you can have more than two where the independent variable is being classified. Because of furthermore assumptions, okay. So the observations what we make should be independent of each other. Okay, there is no relationship between the observations in each group or between the groups themselves. Because if the one participant having similar characteristics and all, then what the idea is, it's not a good idea. The result is having some problem there. So instead of if there are such issues are there, then what is the different statistical procedure. The another part is homogeneity of variance. That means what you call when you talk about variance level, you should be equal in all the suppose you selected three groups, the homogeneity of variance should be almost same in all the groups. And how it can be identified using if you are using the software, the test of homogeneity is making out it's a Levens test. LEVENS. So Levens test is handy for calculation of homogeneity of variance. Then, by chance, if homogeneity of variance is not established, then you have to carry out additional statistics like Wells ANOVA. Then it gives suggest homogeneity, readjust, and then use the unknown value. So that's why you be careful about this. So if the homogeneity of variance is not established, so instead of one way ANOVA, better you proceed for Welsh ANOVA. Okay, that's this one. So that again, what you are telling all this in the minor level, because especially when it comes to the application part, nowadays the peer review is very good, especially in listed journals or standard journals. So I am telling you the minor aspect so that your application should not come for revision or rejection. So if you do take care of all these things, then it will be better for you. Then few more assumptions like there should be significant outliers. Now what happens? The outliers will spoil what you call the significance level. They are given. Usually we find what you call IQ. Again, IQ I'm taking. So in IQ, what happens? Usually we expect the range between 90 to 110. But suppose the student goes 156, it is above genius level. So that is very unusual. So what happens is 150 score. When you treat with the others, your standard deviation goes very high. Once the standard deviation goes very high, the standard deviation scores also, once you convert it to variance also will be high. Thereby, though you are bound to get a significant difference, because of the outliers, you might lose your significance. So that is why. Because once you find what you call outliers are known, that will be very much question for validity of your results. So that also what you call you have to be very careful. That is why we say the different variable or your continuous variable approximately normally distributed for each category of the independent variable. So within subgroups also we are not going for doing each particular individual overall normality. You are going for subgroups also. So within the subgroup also there should be what you call normality assumption should be confirmed. So that is why then if you do that, because the more you do such procedures like you call first what you call, then it's good for you. Otherwise, if you are violating the results, then That's the problem. So that's the idea, and let's set up a chapter with 15 less, more means followers minimum. So knowing all that background, what is called, we go for different types of ANOVA. So usually that one ANOVA, univariate ANOVA, multivariate ANOVA or MANOVA, and then repeated measure ANOVA, that is RM ANOVA or UNCO. So these are the different types. Now before getting into that, I would like to talk about something about post-op test. Then we will call, or we will come back to this post-op test later. We will start with the one-way ANOVA. So when we talk about one-way ANOVA, as I said, it's a typical extension of independent sample sequence. Now earlier what we have done is we have taken two groups randomly drawn from the population and we try to establish a mean difference between them. But in one-way ANOVA, we take a minimum of 3 groups or more than 2 groups and then we try to establish a mean difference between them. So here you will see, I have taken 3 groups, urban, rural and semi-urban. So now the idea is, we are trying to establish, again as I said, attitude towards the free schemes given by the government. So now, whether these 2 groups differ in their attitude, the urban differs from the rural and whether the difference exists from these 3 domiciles, right? Urban, rural and semi-urban. Now, idea here is, remember, when we talk about one ANOVA, it is like extension of features. In fact, you can do multiple features. What are those multiple features? You can check group 1 against group 2 as one feature. You can check group 1 against group 3 or against group 2 versus group 3. So 1 to 2, 1 to 3 and 2 to 3. But you have to do 3 times independent samples features. But to avoid that, at one shot, you can go for one-way ANOVA. So that's the idea. And how it will be done? Now, if you see here, entire the procedure is quite different. Entire procedure goes in 3 parts. The first part is calculation of sum of squares for various things, within groups and all. Then the next part is drawing the table, and the third level we try to interpret the results. So now you see one ANOVA, this is how you get the table. So we calculate sum of squares to the specific position, and the sum of squares is divided by the degrees of freedom, and you get a mean square. Likewise, you go for between groups. Then once you go for between groups, again you get a sum of squares, and the sum of squares is again further divided by the degrees of freedom. Then you get the mean square between groups. Then you have got the error. This one, how this comes based on the total and the error. That is not considered much. But here, one ANOVA, as I said, what we do is if you see the F value or the Fisher's ratio, this will be calculated by mean square of between groups divided by mean square of within groups. So that means if mean square of between groups is higher than mean square of within groups, then you might get your ANOVA value or F value significant. If the within groups, within groups variance is more than between groups, then you might get a non-significant difference. But remember, when you get this within groups, significant within groups is more value because when the variability within the groups is more, then automatically there is a chance of losing the significance. So that is what you have to really see in your selection of sample and applicability of the tool. Because when why you get more variability because if the samples which you selected not homogeneous in nature, then definitely you might get within groups variance more than between groups variance. So usually we expect in ANOVA, between groups should be more, the variance should be more than the within groups variance. So that's the idea. So now, if you have F value is significant, remember I am talking about the double degree of freedom because you get one numerical degrees of freedom, and the one is the denominator degrees of freedom. Numerator is nothing but between groups. Suppose you got 3 groups, you get n minus 1, that is you get 2 degrees of freedom. Then your denominator, so denominator is again n minus 1, number of values into each minus 1 into that many groups. So it is n minus k. So you get double here. Now, accordingly, in the F distribution table, in the significance level, you have to check both in columns and rows. Because in all other cases, you have what is called just checking a single DF. But here in ANOVA, there is one ANOVA, two ANOVA. In each stance, you get double DF. So, based on the double DF, again you have to check your value. Again, the rules are same. If your capital value is equal or more than the table value, then it is significant. If your capital value is less than the table value, then it is not significant. So, you manually calculate or you calculate through what is called software or online. Then you check your capital value against the critical value which we discussed earlier. So, it should be equal or more than the table value. Or your capital value should be equal or more than the table or critical value. Then you say it is significant. But remember, in ANOVA, there is a double DF. One is the column DF and the other is the row DF. And usually the smaller DF we check in the column and the bigger DF we check in the rows. So this is the procedure we got to follow. Then comes what we call post-hoc test. Now, usually we refer one ANOVA as macro level of testing of field difference. Whereas post-hoc test comes as micro level of test. Why? Because to perform and one-way ANOVA, and if you get F value is significant, and if you have got only 3 groups, the F value tells that there is a significant difference among 3 groups. But it will not tell whether mean difference between 1 to 2 is different, 1 to 3 is different, or 2 to 3 is different. To do that multiple comparisons and individual pair comparisons. So, once your F value is significant and if there are more than 2 groups, the next level at micro level testing, that is called as post-hoc test. And usually we don't do post-hoc test when the F value is not significant. So only when the F value is significant, furthermore to see which of the main differences are significant among 2 comparisons, then we go for a post-hoc test. So what happens is it is a multiple testing problem because each particular analysis effectively as statistical test. So you do initially a larger test called as what we call ANOVA, one-way ANOVA. Then you start classifying A to B, A to C, and B to C. Each one has independent procedure. So that's why it is effectively each of them will be statistically managed. So we use the multiple testing procedures. Now, sometimes what you call, if you do that, there is a what you call medicine also is there. Okay? If you do that, what you call, you implement without adequate consideration of this problem, sometimes called as data trading is unnecessary. Right. So because statistical assumptions that finds are often spurious. Sometimes you may get difference, sometimes you may not get difference. But anyway, that is one important for us. But remember, whenever the F value is significant and there are more than 2 groups, it is better to go for a post-hoc test. So we say that integral part of ANOVA. So I already explained this. ANOVA is not identified which particular difference between the papers is significant. So we have to use post-hoc test to find out which of the what we call which of the particular difference between the papers is by post-hoc test. So some of the softwares gives you what we call many what we call such post-hoc tests. For example, Express gives around 8 to 21 types of post-hoc tests. Again, there are what we call rules specific and there is some rules. But usually, what I find is one of the seen in journals and all. I'm trying to avoid 2 tests, that is LSD and DMRT. LSD is PLS also they call, that is piercing service significant difference, and another is DMRT or Duncan's multiple plane test. So some of the journals they do what you call consider if you do LSD or DMRT. So please be aware of that because this LSD and DMRT they give significant mean differences even for a small mean difference, which is not the case in the following later one. So, some of the journals they say, please don't use what you call LSD or EMR. Whether they use it, they might send you back. So, be careful about it. So, the better tests are Sheffield's HSD. So, Sheffield's HSD stands here for honestly significant difference. Then Tukey's post-op test, Bunbury's test, as well as Connect's test. All of these are regularly used as in many journals, depend upon the condition. So it is your choice to use one of these. Sometimes this post-op test depends upon equal size samples in all the system, then you have a specific one. When there is unequal number of samples are there, therefore we may have to use a different post-op test. I will go very seriously about the post-op testing. So that's about one-way ANOVA and post-op test. Now slowly moving to univariate ANOVA or two-way ANOVA. So what happens in what you call two-way ANOVA is we now extend the ANOVA. Remember, in the one-way ANOVA, we have one independent variable split into minimum of 3 levels. In independent sample sequence, we have one independent variable split into 2 levels. For example, in a t-test, we give male female. In one ANOVA, I give the example of male, female, and transgender. Or there it was urban, rural, here it was urban, rural, and transgender. Only single variable was split into more than 2 levels. But in two-way ANOVA or univariate ANOVA, we use minimum of 2 variables, independent variables, and one dependent variable. So I wrote that dependent variable as attitude towards the common schemes. So that is the dependent variable. Here also in two-way ANOVA, what is called is the extension of one-way ANOVA. Okay. So there are two independent variables. So for example, if I say urban, rural, and what is called the semi-urban part, you have got first variable split into 3 levels, and second variable will be split into 2 levels, male and female, urban female, rural male, rural female, semi-urban male, and semi-urban female. So your design will be 3 by 2. So in such cases, where you have two independent variables against an independent variable, against a dependent variable, then you can go for a two-way ANOVA, or sometimes the latest terminology use this univariate ANOVA. Remember, when you talk about univariate ANOVA, the univariate word stands for what you call a dependent variable, not for independent variable. Univariate. The later we are going to talk about multivariate. So let's not go right now. A simple example for what you call a two-way ANOVA. So you are measuring performance in an industry with the salary and scale. The salary goes get high, medium, and low. The salary is what you call split into 3 levels, and the skills are split into only 2 levels. And remember, each of the individuals are different. They are not the same. All the individuals are different. Because it does mean that the statistics will be different. So the groups what you have formed are different from each other. They are independent observations. So now this is the typical example of 3 by 2 design. Because salary is split into 3 levels and skills are split into 2 levels, thereby making it a 3 by 2 design. Now how the table goes. So you have factor A as salary, factor B as skills, then we have an interaction effect, which is there exclusively when there are what you call univariate ANOVA, because we talked about interaction effect. So the interaction effect needs to be considered because it has got a good opening for what you call interpretation. So you as usually calculate also variation, like you have between salaries, between skill set, and you have got a source of variation for salary, skill set, as well as interaction. Then accordingly calculate degrees of freedom. Remember, in one ANOVA you have got only one F value, but in two ANOVA you are going to get three affairs. So what are these three affairs is? Okay, if you go back to the example, one is the performance difference across salary class, high, medium, and low. Then the second one is FL for the skill difference between high and low. And the third FL is interaction between salary and the skill set. So you have got three FL, and you can see how it is being calculated in the formula. So this is how we calculate. Now we just slightly extended more than the one by another, where you get separately one F value for the first variable, you get separately F value for the second variable, and you get an interaction effect between the particular salary and the skill set. So this is how you go for three-way ANOVA. Now remember, I can continue three-way ANOVA, four-way ANOVA. Now remember, all these are called as univariate ANOVA. Why? Because in univariate ANOVA, that is univariate ANOVA, we remember it as for a single dependent variable, again, two or more independent variables will be free to become a univariate ANOVA. But parametric classes is not just that much. We go for multivariate ANOVA or MANOVA. Now remember, in MANOVA, what we do is we have what we call several independent variables versus several dependent variables. This is something tricky. That's what's called as MANOVA. So all the time we talked about one dependent variable against two or more independent variables. But when it comes to MANOVA, we have several independent variables versus several dependent variables. So this is where the trickiness comes. Now remember, earlier we had what we call two variables, independent variables we decided. One is what we call, one is the area or the domicile, urban, rural, and semi-urban. Within that, we consider the sub-variable as male and female in each. That is two independent variables. Against that, what we call, we check what we call the attitude of the what we call people. Now, along with the attitude as dependent variable, I can add more of quality of life. That's another measure I am adding as dependent measure. I am adding aptitude, quality of life, aptitude, family support. Now I have four variables on the dependent side. So you have now here two independent variables and four dependent variables. Now this design would be in parameter statistics is called as MANOVA. Now remember, as usual, you get individual F values for R. You get individual F values for R, but the one simple idea is whenever you say or imply that you have performed MANOVA, please don't forget to include one of the index called as Wilks lambda. So Wilks lambda is one of the index which gives the idea of influence of all the independent variables over the selected dependent variables. So Wilks lambda is one of the index which you have to invariably you have to give or you have to provide in the article or in the presentation or in your work whenever you perform MANOVA. But remember, it is quite easy. That's why you have to use any formula because it's a lengthy procedure. So it is basically several independents are versus several dependent variables that are treated and you derive what is called three of the indices. Individual as well as anyway you are going to get, but along with that you get additional. So after MANOVA, we are going to discuss repeated measure ANOVA. Now, repeated measure ANOVA is again extension of what we call pair sample treatment. Remember, in pair samples, I gave the example of pre-post. So you have got a pre-test, you give some information, and you have got a post-test. So now what I am doing, repeated measure ANOVA is, as I said, the same subjects are being employed. Remember, pre-test, ABCD are being employed. The same subjects are being employed in the post-test, and you are interested in what happens in the follow-up. Then the same measurement, what we call has what is called the measurement has continued over repeated over at least 3 sessions, it could be 4 or 5, doesn't matter, on the same subject, then it becomes repeated measure ANOVA. So once it's repeated measure ANOVA, that's why I said it's the extension of what is called fair sample status. This is the one condition where you can apply the repeated measure ANOVA. You have pre-test, follow-up, post-test, and follow-up. And sometimes we apply what is called repeated measure ANOVA when you have got experimental and control group as well as pre and post test. But sessions are only control group, so the session is 2 by 2. Pre-test, post-test, as well as experimental and control. Still you can apply what is called repeated measure ANOVA. Provided in pre-testing you have established randomness or matching of the groups between two groups. That means in the pre-test, both experimental and control groups, the mean value should be statistically same. Then whatever changes are happening in the first test, that can be attributed to the intervention or the training part of it. So this is how you go for a repeated measure ANOVA. Again, we can do 3 times fair sample pre-test, pre to post, pre to follow, as well as post to follow. So that's it. So this is where we talk about repeated measure ANOVA. Then we have analysis of correlates where people have to use this. Now in research, we find what we call one of what we call variables which are not directly what we call connected to your what we call research. But what happens sometimes is sometimes there are confounding variables, intervening variables. These variables or extraneous variables, these variables have influence on the outcome of your results. Or when you do analysis and at that the results would be different than what is expected. Why? Because the influence of what you call is extraneous or intervening or confounding variables which might include into the process of experimentation or data collection and thereby change the end result, change the direction of end result. So in such cases, you have to be very careful. You have to use ANOVA. You have to somehow quantify those effects come from extraneous or confounding or intervening variables. Quantify them and use them as covariates. So once you use them as covariates, then you can control the effect of this variables. So then it will be much easier. Or sometimes what happens is sometimes you are not able to establish what you call non-significant mean difference between experimental and control groups to see the final effect. So when there is what you call matching of group is not there, then still you can go for ANOVA. Still you can use the ANOVA, taking pre-test scores themselves as covariates. So that's the idea. So in such cases, there is a screen, you can check it. So there are no conditions which will apply when you feel that other factors are influencing other than the factors employed in your research. Better you go for ANOVA rather than ANOVA for differences. So that's the idea. That's why it is most of the difference based tests. Now quickly we have to finish the relationship based parametric. So whenever we talk about the parametric relationship based test, we talk about basically correlations and the regressions. So in correlation, we are going to talk about basically product moment correlation quickly and a partial correlation. I will tell you the conditions. Then regression, there are 2 types of regressions we are going to talk about: simple and multiple regression. Now, a correlation coefficient, especially on a parametric side, is nothing but measurement of mutuality or dependence of one variable over the other variable. So that's the idea. How much what you call the dependence is there, percentage direction of relationship between 2 dependent variables. And usually the small sample population we use the smaller and for all we use for the population correlation. Now what are the possible relations you can find? So there is a direct cause and effect relationship. So something is there is a cause and there is an effect. So more physical exercise, better the activity. There is reverse corner effect relationship. Second type, where more accurate usage, more anxiety, or more, sorry, reverse corner. More accurate usage, lesser the sleep quality. So one increases, other decreases. Then a relationship between the variable will be caused by the variable. Now we call the mediation effect. So you have the cause and your effect, but something in between is what we call intervening. Thereby, the end result will be different. Then there is oppositional interrelationship. So multiple relationship among many variables, and sometimes the relationship between just coincidental. Okay, it happens sometimes. Something we call them as spurious correlations. So when we talk about types of correlations, we talk about simple, multiple, and partial correlations. R, capital R, and V are respective usages. And when we talk about the directionality of the correlation, the user will find a positive correlation or a negative correlation or no correlation or no relationship. So graphically speaking, if you see what is called a perfect correlation as the x increases, because you need two variables x and y. So as the x increases, y increases also. But what the graph has shown is a perfect correlation, which you may not get in your research. There should be a perfect negative correlation. Okay. This is where you can find as the x increases, y increases. Now on a similar any other research, you can find a positive correlation where you can see the dots are scattered plots. They give the idea that a positive correlation how it looks like as x increases, y increases also. And then the negative, like as x increases, y increases. So these are the things. And sometimes you say no correlation, the scores are just correct. We cannot predict one from the other. Specifically in the research, we use the product moment correlation. So basically, in the case of product moment correlation, we measure what we call whether the function of two random variables from independence, how much they are related or they are deviating away. So here we don't talk about the word difference. Here we talk about the word relationship. So there's a major change we are switching over. And remember, as we do to apply Mason's product moment correlation, normality has to be established first. Then the rate of correlation usually we find is -1, which crosses to 0 and ends up at +1. So in the regular calculations, if you get your correlation coefficient as more than 1, take it for granted. It's a wrong calculation because you have done a wrong calculation. Usually software will not do such a wrong calculation. But if by chance in manual calculation you get more than 1, then it's not a right one. So the rate of correlation is +1 to 0 to -1. Where +1.00 is called as perfect positive correlation, whereas -1 is called as perfect negative correlation. And remember, in reality, I think exactly +1, exactly -1, and exactly 0.00 is difficult because the correlations lie in between these. And interpretation goes by sample size. More the sample size, even the smaller correlation coefficient would be significant. Lesser the sample size, the higher correlation coefficient will be not significant. It can happen like that. So this is why you have to be careful to employ sufficient number of samples. So that is more important. And sometimes you don't want to get correlation, but you get correlations, and those correlations are called as spurious correlations. So just keep it in mind, these are called as spurious ones, which are not required. So how do you calculate the correlation coefficient by product moment method is one of the formula. It is you have x and y variable. Later you square each of x to get x square, square each of y to get y square. Then you multiply x into y to get x square. So if you have this and then you can directly calculate correlation where r is equal to n into sigma xy minus sigma x into sigma y divided by square root of n into sigma whole square minus sigma x square minus sigma x whole square one fraction into n into sigma y square minus sigma y square y whole square. So if you precisely enter the values and if you calculate stepwise, you get a correlation coefficient, and later you have to check against the table value depending upon the sum. Here again, when you talk about the PF, please remember here PF is equal to n minus 2. So please remember in only two cases in non-parametric viewpoint PF is equal to n minus 2. One is in independent sample stages and another one is PF's product moment correlation. By the way, there are several other correlations formula there. I'm just giving one of the sample particular formula. So PF is equal to n minus 2. Next we have particular regression. Okay. Let's not talk about the meaning and all. Usually in dictionary we see regression means going back or return, but in statistics the regression means moving forward. So here regression basically amounts for prediction. So a lot of predictions are happening. I'm not talking about the election prediction. There is no regression, but a lot of these companies, their growth, their sales, marketing, everything is based on one of the particular technique called as regression. Suppose Infosys tomorrow calls for a meeting, director meetings, and say in the next quarter our particular our projected projected growth or projected profit is 600 crores. That means this value is based on the previous few quarters results, and you take those into consideration, and then you calculate what would be the projected or the predicted particular profit. And in such cases, we talk about regression. So you basically try to predict. So regression is nothing but extent of relationship plus how much rate of change occurs. So rate of change occurs should be increase or it should be decrease. So that's the idea. That's the meaning of regression. Or it's basically a report for a forecasting. Then why is it important? Now, there are three points you can tell. We provide an estimate of values of different variables from values of independent variables. That means if you have a regression equation, then you can calculate further. If let's say you already predict y value from the x value, where we y as the dependent and x as the independent variable. So you give x value and you can predict y. Then it can extend it to any such variable, and in that case, instead of simple regression, the idea would be multiple regression, which will be discussed in short. Then it shows the nature of relationship. It just not only shows the relationship, it shows what the magnitude of change. That's also important for us. So having that, what are the types of regressions commonly employed in particular research? Now, simple regression as well as multiple regression. Remember, logistic regression I'm not going to talk much because it involves on the non-parametric side. So let me concentrate only on simple regression as well as multiple regression. We'll move on to the simple regression where you have one x variable and you have one y variable. Now, y variable is considered as a predictor variable, x is the independent. Now, you see, we have this one as the x increases, y also increases in the first graph. In the second graph, you find as the x increases, y decreases. Now, what are the concepts maybe? Remember, if you see those dots or the scattered plots, they are actually the original values. The regression procedure prints an equation y is equal to a plus bx, and later after recorrection, a straight line will be based on the directionality of the data. So since there is a positive direction, you can see the red line going straight up in a diagonal way. So that is what there is a direct relationship and the rate of change is very high. Whereas see here, the same particular idea is shown in other graph, but the decrease is not as much as the increase you find. So the concepts are very different. That is what similarity is less here, the similarity is more here. So that's the idea. And then a formula is there. For simple regression, you have y is equal to v0 plus v1 x. Each website and different one. Sometimes it's y is equal to a plus bx. the multiple linear regression, it is V0 is the constant, V1 and X1. V1 is the rate of change, X1 is the first variable, V2 is the rate of change for the second variable, X2 is the second variable. Keep on going till V1 into Xn. Whereas polynomial is a non-part of square variables, we will not be interested. So we will see whatever the regressions which are done either by simple linear, where you have only one example, whereas multiple regressions, you have several axes and one y. Now the y is capital and called as major dependent variable. So that's the idea. Now in simple regression, you can see this working as the years of experience increases. What happens to the set? As usual, we find a linear regression. Now you can calculate after calculating the equation y is equal to a plus bx. You can calculate if 1 year is particular distance average increase. What will be the 10th year? What will be the 20th year salary increase on a hypothetical return? So this is the beauty of regression. Then moving on to next, we will talk about multiple regression. So multiple regression is usually called as extension of simple linear regression, where you will take several independent variables and we call it as against variables on one dependent variable called as major dependent variable. Sometimes we use the criterion variable, sometimes we use the word outcome variable, or sometimes we use the word target variable. So all the words are from the same. And what are the procedures we follow? So it will be structure presentation or algebraic presentation. In there, there is a pre-answer procedure, list procedure, and even in algebraic form, there will be least square, there will be deviation from arithmetic mean, there will be deviation from assumed mean. But usually, what I find in our regular teaching, we go for method of least squares. So this is one as I said, use y is equal to a plus bx or bx plus a. There y is the parameter predicated, b is the slope of the constant rate of change we call into x the value to be input plus a is the constant value so by input. So by doing that we get the value of y. So then furthermore, what is the algebraic method? We already discussed what exactly happening. A plus bx and I have explained already. But let us see more into the multiple linear regression. Now already we are saying linear regression, one x and one y. But in multiple linear regression, we have got x1, x2, x3, x4 against one y or capital Y. So now it is a technique that several estimated variables to predict outcome on a response variable. So what is going to happen here is it gives a lot of explanation, and not only that, how much is contributing. Now to make it very simple, using method of partial discourse, now show the example. A student academic achievement, if we consider as what we call a major, what we call dependent variable. For example, I will side and take the color out here. So, a student's academic achievement would be what we call influenced by several factors which are I'm just going to hypothetical example. Several factors. Which will be heredity or IQ. It can influence a lot. Our classroom environment is another important thing which can influence better achievement for the student. Amount of Android or mobile usage can influence academic achievement. Examination anxiety to be another factor. Number of study or academic the student has put it influence on the academic achievement. Parental support is also important. The support comes from the parents. Motivation to study and achieve more can influence academic achievement. Peer pressure, either to good or bad, can also have an influence. I'm just putting some 8 variables, dependent variables or the major independent variable. Major dependent variable as academic achievement and independent variable as heredity, classroom environment, Android usage, examination activity, number of study hours, parental support, motivation, peer pressure, all that if I reduce some academic achievements, only a few factors may come out as predictors of what we call academic achievement of the student. Not all of them will predict, few of them will predict, and once they predict, then they say what percent of heredity is predicting Because I can say now, looking at this, at least three variables out of eight, that will be more. At least three variables out of these variables are going to predict by our analysis psychology. So, heredity could be number one because the time part we can play later. Powered by Android usage, the more mobile usage, the number of study hours may not impact on the academic assessment, and it says how much percent is being contributed by each. So they may contribute 70%. You look at the equation and the analysis and the addition after it. But then you are taken with another 30% of the area is contributed by the factors which are not really said that not from elsewhere. So that's what we call it as a result. This is called as multiple regression. Several independent are regressing and finding out which are the best predictors of your criteria or a target value. So this is the formula. Function given in Excel, and all that are given. So it's a different variable. X is the exponential variable, y is the intercept, which already know that's a constant. Then P is the slope of coefficient from each exponential variable, which are contributors, and is the error term, not the known as the ratio. So if you have this, you can have a beautiful equation, and you can calculate contributions from each of the predicted variables. So most of the particular could be very much useful. Even useful for policy meetings. A few of the policy meetings are come from regression analysis or type of regression analysis. Why? Because today some of the our regression bicycle scheme or midday wheel scheme, and we see there is a definitely reason behind. Maybe somebody must have done a research. What makes students absent from the class? What makes one they must have collected several parameters, poverty, distance, parental residency, and all that. Then they will replace on the aspect of attendance. Now they have come out with the three of the factors, exactly like one the distance and the poverty. So to reduce the distance, if the bicycles are given, then I think they are pretty distance. Bicycles to a big group of teachers start with the girl child, then let me the boys also, so that the comfort is increased. Pretend is, but they not just come for the schools, just for eating, they come for classes also. So the government for that matter, their goal is achieved. That one thing is increase the punctuality and educating the girl child as well as others. So this was the basic idea behind, but this was due to make one of the statistical calculations. So this way is regression works for you deriving the schemes. Last few slides, so already we are approaching the time. So we talk about significant, non-significant. So how to interpret significant errors? So the significant errors is interested at three levels. That is, your result obtained based on the test value. The test value of the critical value which is there in the table are shown either as significant at 0.0511 or significant at 0.017 or significant at 0.001. So that will mean that at 0.05 or 95% confidence, the meaning is that if you repeat the experiment 100 times, 95 times you won't get the same result. 5 times, we can use the result. So that much is surety, the confidence here, 95% confidence. This is a significant criteria for success. Whereas the regular class of is 30 or 40, but in science is 95%. So, to be 95%, economic is significant. Even if it is 94 out of 100. So, when we talk about highly significant, that means now it is 99 out of 100. Only one time you get this. The severity goes high. And very highly significant, it is 99.9%, that is 0.001. According to what is of the change, very highly significant, out of 1000 times, 990 times. So as the levels increase, the severity of the Then the first one as well as what you call the distinction. So the same how we get the weightage in the colloquial word in the given research to give the technical wordings. So that's what I want to discuss about the significance. Then we are talking about the network verification and all. As I said in the beginning, another methods are usually meant for acceptance or rejection. Alternate methods are meant for the null methods are meant for acceptance and not sorry, null methods are meant for rejection and alternate methods are meant for acceptance. If you have proposed null hypothesis and your results are significant, that is that more than the typical value, then you select the null hypothesis. Sometimes if you propose a null hypothesis has no difference and your results are not significant, you get no difference, you are accepting a null hypothesis. Sometimes whatever your formulated alternative direct hypothesis and whatever you said is not being seen by certain, then you accept the alternative or direct hypothesis. And sometimes whatever you stated is not happening by the statistics, then you reject your alternative or direct hypothesis. So this is how you verify the hypothesis. But sometimes what happens? Sometimes there will be errors in acceptance and rejection. That will lead to errors. And that's that errors are called as type 1 and type 2 errors. So remember, more type 1 and type 2 in your research might end up in the revision of your article or revision of your thesis that we get the knowledge. But type 1 has one hypothesis and the tested hypothesis is falsely rejected. So to give a simple example, it is when you say you want something but the something is really an error. So we say type 1 error is a false positive, right or what? Then you have type 2 error. What happens if the false tested hypothesis is not rejected? It is when you don't find something that is in fact it is there. So I'll give an example, then we'll say example for type 2 error is a false negative. So these are the two types of errors we commonly encounter in research. So what you call and just for about example for type 1 is false alpha bogus effect. We'll talk about that. Reject the null hypothesis is really then type 2 error is a real effect. Wait to reject the null hypothesis is really false. The last type of the what you call synthesis lazy, incompetent, unhelpful, ignorance of the truth, if the research error, then it will be type 3 error. But this type 3 error not be found anywhere, it's somewhere very rare to find in textbooks and all, but type 1 and type 2 errors are very common. So examples for type 1 error. A file error going on indicating file error when what you call in fact there is no file. So you keep building file error modules and you find that only alarm is there, but alarm is there, but there is no fire. That means what? Something is not happening. What you call which is shown as happening. That is type 1 error. There are other examples. Whereas type 2 errors, there was fire, but no alarm. There is something succeeded. A fire breaking out and the fire alarm does not ring. So these are the types of errors you can avoid. This is what a technical error in hypothesis verification. Try to avoid. With this, I will be concluding my talk. I'm sorry I was under 3 minutes, but anyway, if there are doubts, feel free to ask. Some quick doubts, I can put in the chat box also. No questions? Expert or questions? Okay, go ahead. don't know the camera. I cannot see your face. I'm on desktop. Oh, okay, no problem, no problem, no problem, no problem. Thank you so much, Nancy, given coming to information to our participants, and really thanks to you. And it was a great requirement. I was also the one to know. But also I was a little bit here and there, man, and work and other thing. However, I know you would be able to present the best thing, and you are an expert in the field of this. And I want to share one information with you. Yes, sir. Some of the participants who asked me that if Lancy and Bono is presenting the thing, then I am definitely join the course. Thank you, sir. Thank you, sir. Okay, sir. So soon I'm sharing the PPT, can be shared with all the participants. Okay, then good thing. Thank you. Okay, sir. They can get back to me anytime over email or not register. Email they can always contact. Okay. Thank you. Thank you, and all the faculty and the management of Chandra for giving me this opportunity to interact with you for 2 hours. Hope I didn't annoy you. Okay, thank you once again. Okay, thank you. Sir, I can enter that. Address or another meeting.
Very good afternoon, Dr. Vinod. I'm Secretary Assistant Professor, Department of Commerce and Business Administration, PB Center, Hong Kong. So, we are going to pleasure to the full amount of time for this session. Firstly, I would like to express my sincere thanks to today's Zoom person, Dr. Nancy D'Souza, Professor of Psychology, Maharaja College, University of Mysore, my students for sharing your knowledge to all the participants. So, definitely, whatever you have shared your knowledge is our encouraging test, which is very informative and useful for all the participants. Thank you for spending your valuable time with us today, sir. Thank you so much.
Okay, somewhere I have the question, and if you raise your hand, any questions, please. Somewhere has raised their hand. Any questions? Okay, Pradhan sir, if you have a question, you can directly go to WhatsApp. I can answer that later. Okay. Okay, sir. Okay. Please, Tanmay, about the tomorrow's program.
I would like to thank our beloved principal, Dr. Devika, for your support in enriching the faculty development program. Thank you, ma'am. It takes immense pleasure in extending the sincere thanks to Professor Narayana, the Department of Commerce and Business Administration, for his encouragement and guidance in this faculty development program. Thank you, sir. I extend my gratitude to Dr. Jyoti A, Head of the Department of Commerce and Business Administration, for allowing our contribution for this session. Thank you, ma'am. I extend my thanks to all the participants in this technical session. I want everyone to get benefit from this session. Thank you very much. Finally, I would like to thank all the faculty members and technical teams for their support and involvement. Thank you, Linda. Thank you.
We have tomorrow session with the 5. So it's Sunday, tomorrow, 10 to 12:30. The resource phase from the Christ University Bangalore. So we will be addressing this on the topic of machine learning in business, tools and techniques. The topic tomorrow will be addressed. The learning to be shared in the WhatsApp group. So I develop